So today's lecture is going to be about notch sensitivity in fatigue design. And then I'm going to give a few examples just to illustrate how we use the different Marin fatigue factors and notch sensitivity in a couple of design examples. As we discussed before, notch sensitivity is a way to give focus on areas of high stress concentrations. We have learned before that there's a theoretical way to calculate the stress concentration factor, and that it is extensive graphs and equations that are used in design for static conditions. We're going to use this information because it's available, but then we would like to apply it to fatigue design. And in fatigue, the situation is not so dire, because under fatigue conditions, you get plastic deformation in the near vicinity of sharp corners, and that would redistribute the stress, and then the effective stress concentration factor can decrease. So this idea is expressed as a notch sensitivity idea, and I'm going to start from there. So let's see how this works. If we go back to looking at the stress concentration factors as we defined it. So we have defined the theoretical stress concentration factor as the ratio of the maximum stress at the location of the sharp corner or the disturbance in the material divided by the remotely applied stress. So this ratio is a theoretical ratio for tension and for shear. So K sub T is theoretical value. And we know now that we can obtain such theoretical values from many sources, like in Appendix A, 15, and 16. Or if you are in real design applications in your company or in research, then you could use Peterson's stress concentration factors and the manual for that. For example, in shaft design, which is shown here, the shaft is, if we look at it, it has two diameters, lowercase d and uppercase d, and the two diameters are connected with a fillet, and therefore we have three parameters here. And the stress concentration factor is a function of the fillet radius. So the sharper the fillet, the higher the stress concentration factor, and the more generous the fillet, the stress concentration factor decreases. It is also a function of the ratio of the two diameters of the shaft. So we'll use this information in general in our discussion of fatigue notch sensitivity, as we will continue to discuss it here. So in this situation, we're going to define the notch sensitivity factor as Q, and Q is defined as the difference between the stress concentration factor under fatigue condition and unity, because unity is the case when we have no change in the geometry, no sharp corners. So this is the difference, which is the excess, divided by the excess in the case of the theoretical static loading. So this is the excess in static, this is the excess in fatigue, and we will call this the notch sensitivity factor. And in materials Q, if Q is equal to 0, then K sub F is equal to 1. There's no stress concentration factors under fatigue, regardless of whether we have high stress concentration factors under static conditions. That's the excellent case. If Q is equal to 1, then K under fatigue is the same as K under under static loading, and the material or the design is known to be very sensitive to notch. And therefore, if we know Q and we know also KT, so KT we can get it from graphs or tables, and the Q is a parameter that is computed as a result of plasticity calculations and maybe also experimental data. So we will have cyclic plasticity. We will see if we cycle from one cycle to another, how the plasticity decreases the overall stress in the region, in the vicinity of the notch. And that would be the very accurate design. But in case we don't have the ability to do these elastoplastic calculations, then we would use recommended values for Q as shown here. So we would know what Q is, and therefore we are able to compute basically the stress concentration factor under fatigue conditions. So we would have here we'll be able to include that in the case of fatigue. We can write K sub T is equal to well, actually K sub F in this case, because we are interested in the K under fatigue conditions. K sub F is equal to 1 plus Q times K sub T minus 1. So once we know Q and K sub T, then we would be able to determine the fatigue stress concentration factor. If we look, we will look shortly at how Q behaves, but it's basically plotted Q as a function of the notch radius, because it depends on the notch radius, and this function is an increasing function. As the notch radius increases, it goes all the way up to unity. So these are the considerations that we have, and this function can be expressed also as a polynomial function that can be used in a design. So here's the considerations for the notch sensitivity factor Q as a function of the notch radius, and Q depends on the ultimate tensile strength of the material. The higher the ultimate strength, the more brittle the material is, and the higher the notch sensitivity factor as a function of R. And when you have lower and lower values of the ultimate strength, plasticity plays a bigger role, and the steel is going to be less sensitive to notches, as you see here. The dashed line is shown for aluminum alloy. So for each alloy, we have to determine this notch sensitivity factor, and once we determine that, we're able to compute the actual stress concentration factor under fatigue conditions. Here is the results also that can be used when we have torsional loading. So in this case, K sub F is called K sub Fs because it's under shear, and the corresponding stress concentration factor theoretical value is termed K sub T S. Now the Q, instead of we have two choices, either to use the graphs or to fit the graph somehow to a polynomial, and this is preferable because we could do some computations, and then when we do the computations, we are able to immediately use the value of the notch sensitivity factor. It is determined as a function of this parameter A, and the square root of A is fitted to a polynomial in the ultimate strength of the material. So these are all empirical fits for bending or axial, or for torsion, as you can see in here. So once we know the ultimate strength, we can substitute here, find the square root of A. Once we find the square root of A, we can substitute here, get Q, and then once we get Q, we are able to obtain the stress concentration factor under fatigue conditions. In case we have cast iron is very, very sensitive, already full of discontinuities, which is included in the strength anyway. So additional notches do not add much to additional harm, which means that it is kind of counterintuitive that we would think that cast iron would be very sensitive to under fatigue conditions because of discontinuity, because it has high strength and it doesn't have enough ductility to distribute the load. But I think the wisdom here is that it already contains these discontinuities in evaluation of the strength of cast iron. Therefore, the notch sensitivity factor is quite low, given as 0.2. So now we are done with the notch sensitivity factor, and we would like to use it in some examples. So in this example, we will illustrate the process of using equations to determine the notch sensitivity factor, and hence we find the stress concentration factor under fatigue conditions. So we're going to have an example to prepare us to a much bigger example, as we'll see in a few minutes. So in this example, we have a shaft, and the shaft has ultimate strength of 690, and it has a shoulder, and the fillet radius is 3 millimeter, and it connects a 32 millimeter diameter, which is lowercase d, to a 38 millimeter diameter, which is uppercase D. And we want to find the stress concentration factor under fatigue conditions using figure 620 and using the equations. So in order for us to do that, we go to figure A15.9. That gives us the theoretical stress concentration factor, as we discussed earlier in this lecture, knowing the ratio of D, or capital D over lowercase d, and the ratio of the notch radius or the fillet radius divided by lowercase d, and that gives us 1.65. Then next is we want to see under fatigue conditions, is the 1.65 going to remain or going to change, become smaller? So that depends on the ultimate strength. The ultimate strength is 690 and the radius. So if we go to the figure and read it off, it gives a 0.84, and we get the K sub f 1.55, or we could use the equation for the square root of A, that's polynomial in S ultimate, and it gives us the same answer because it's a fit to the same data. So now if we want to apply the fatigue stress concentration factor to design, then what we would do is we take the endurance limit and multiply by 1 over kf. So it's basically we are reducing the endurance limit by kf. So the endurance limit SE prime after 7 factors become SE, and then SE, once we have the stress concentration factor, becomes SE over K sub f. So the reduction could be tremendous in here, from the rotating beam to the actual in the design. So it's a big process, and step by step, once you lose a little bit here and a little bit there, then the final result for the endurance limit could be quite small. So let's take an example here, and the example is that I have a fully corrected endurance limit of 280. That's after the 7 factors, and we have a shaft that undergoes fully reversed nominal stress at the fillet of 260, and we want to estimate the number of cycles to failure. So this example builds on the previous example, in which we are given the dimensions of the fillet, the diameter of the smaller shaft, the diameter of the bigger shaft, and then we are able to compute the notch sensitivity factor from the polynomial, and then use the equations or the figures in Peterson guide for stress concentration factors under static loads. We can use this to find K sub T, and then finally we get K sub F that is required under fatigue conditions. So we are assuming that we applied the 7 factors, got the SE, and on top of that we found the exact value of the stress concentration factor under fatigue. Then the final result is that SE now has to be reduced even further by when we divide it by the stress concentration factor under fatigue conditions. Having done that, then to estimate the number of cycles to failure, we use the correlation that we have, the power law correlation that we have developed, in this case for high cycle fatigue. So that's kind of the process that we have here. We want to estimate the number of cycles to failure, so we have to test it in both high cycle and low cycle fatigue. So before we go there, then the applied stress is now the nominal multiplied by the stress concentration factor. So we amplify the applied stress by a little bit, and then we obtain 403 megapascal. And having worked out the fraction F of the ultimate, and we know the ultimate, and the endurance limit is also corrected for the 7 factors is 280, then we get the constants A and B, and then we are now assuming that we have conditions that can be described as low cycle fatigue. So that's why we're using these equations for low cycle fatigue. We estimate the number of cycles to failure. We find that this is 32,000 cycles to failure, and therefore this estimate is somewhat outside the bounds of low cycle fatigue, and I have to repeat these calculations for high cycle fatigue. And high cycle fatigue, we have another power correlation for A and B, and we use that to find the number of cycles to failure. So if we now move on to another example, in this example we have a hot rolled steel, and it's machined from 1-inch diameter bar, and it's placed under axial loading for 70,000 cycles to failure, and it operates in an environment of 550 degrees Fahrenheit. So we wanted to use ASTM minimum properties with a reliability of 99% and estimate the endurance limit and the fatigue strength at 70,000 cycles. So if we solve this problem, we go to table A20, find the ultimate strength at 70 degrees F, and then we estimate the ratio of the ultimate strength at temperature divided by the ultimate strength at room temperature by interpolation, because we're not given the value of the exactly at this value of the temperature at 550, where we have to interpolate between two different temperatures and estimate the ultimate strength on that basis from the factor, and from that we multiply by half to get the endurance limit under these conditions at temperature. Okay, so let's say we want to determine the Marem factors for the machine surface. We have to determine K sub A and that's for our case here. For the ultimate strength is given, and we know the two coefficients A and B from the previous table. And since we have axial loading, so the load factor is 1, and the size factor is 1. And then because we have axial loading, then the load factor is 0.85. Temperature factor is 1. And also for the reliability, if we want 99% reliability, then the reliability factor is 0.8. Miscellaneous factor is 1 because we don't have any other information. Multiply these 7 together, we go from 24.5 to 16.3. So it's a kind of a drastic reduction in the rotating beam value to the actual value as a result of these practical Martin factors. And once we determine that, then we know the number of cycles to failure is given, and then we want to use the SN construction, and here since S ultimate is is 49, so it's smaller than 70, we obtain the fraction of the ultimate at 1000 cycle, and we obtain the A and B coefficients, and therefore we solve and find the fatigue strength at 70,000 cycles. Now this is the last example that we're going to give here, and in this example, this is a good example because it shows us kind of part of the process of design that we're going to use in larger examples when we do shaft design at the end of this course. So as you'll see, we'll have a real shaft, and it has shoulders to attach gears, and then we want to find the fatigue life given that we have some kind of a force system on it. So in this case, I have a rotating shaft, and it's simply supported in ball bearings at A and D. So I have two reactions, R1 and R2, and a force of 6.8 kilonewton, and given the dimensions. So from that, if I just write equilibrium equation to have the sum of these two equals to 6.8, and then we can take moments around any one of these points, like this point or this point, then we find R1 and R2. So these are determined. Once we determine that, then we can construct the moment diagram. So we want to actually design this whole shaft for fatigue. So once we do that, then the moment diagram is going to go from 0 moment on both ends to a maximum, and the maximum is under the concentrated force, and therefore the moment diagram is going to be linear from 0 to the maximum. Now if we look at the worst condition in here, we need to kind of think about, if I need to do fatigue design, where am I going to look at fatigue? Well, fatigue will be a result of a fluctuating moment, because as the shaft rotates, the tough fibers will undergo tension, and then in the next half cycle they will undergo compression, and then tension again, compression. That's how the cyclic loading comes in, and that happens all along on all of the entire beam or entire shaft. However, I don't want to do the fatigue analysis everywhere. I want to select already the most critical section of the shaft and design for fatigue life. So in this case, I have choices, either to look at where the moment is maximum, or in areas where the shaft radius is the smallest, or in areas where I have highest stress concentrations, or a combination. So if you look at here, I have the moment is maximum exactly at this point, but the shaft is thick. However, the moment is reasonably large, and the shaft decreases in size, and then it also has a shoulder here. And then if you look at M sub C, the same thing happens here. So I select either M sub B at point B, either at point B or at point C. I would have to prefer point B for two reasons, because the shaft diameter is small as compared to point C, and also the value of the moment here is higher at point B as compared to C. So based on these decisions, I need to compute the moment at point B before I move any further. And that we'll do like in a few minutes. And then once we find the moment, then we find the sigma due to bending at this point, and then use it in the design. So we'll set this aside. Next is that we want to get the strength data from the table A20. We have the ultimate strength 690, the yield stress strength is 580, endurance limit is half of the ultimate, 345. We have the Morin factors are given here, surface factor, and we have size factor, and then the other four are not given to us, so we're going to assume that they're equal to unity, and therefore the fatigue endurance limit is reduced from 345 all the way down to 236. And that's not accounting for stress concentrations, because we will account for stress concentrations in amplifying the applied load or applied stress. So next is the idea of stress concentrations. So I have to find K sub T first with the ratio of the diameters and the ratio of the fillet radius to the lowercase diameter, and that gives me 1.65. And then since the ultimate is known in KSI, then I can find the correlation, use the correlation for the square root of A, and hence K sub F is computed to be 1.55 compared to 1.65 under static loading. So there's a little bit of relief from fatigue spreading plasticity, but not too much. Now the moment at point B is computed by taking the reaction that we computed times the distance, and that's 695.5. And then to compute the bending stress, I need to find the section modulus I, the section modulus I over C, and that is pi d cubed over 32, given the value here. And therefore, normally I have the bending stress, maximum bending stress on the top or bottom fiber as the moment divided by the section modulus, but here we have to amplify it with the fatigue stress concentration factor of 1.55. So the sigma reversed is 335.1. Once I determine that, then I can go and find F from the ultimate strength of the material to be 0.844, and find the two coefficients A and B, and plug in and find that the number of cycles to failure is 68,000 cycles under these conditions. So we have now learned a procedure by which we can do reasonably sophisticated fatigue design by going through all of the successive Morin factors one by one, estimating them from the correlations or the graphs, and by looking at the notch sensitivity, finding exactly the value of the fatigue stress concentration factor and amplifying the applied stress at that point here. In real practice, as we proceed in the course, we're going to have to consider torsion, and we consider axial loading, and that will complicate it because we would have to consider multi-axial loading effects. Not only that, but if I have a steady type of loading on the system, such as like an axial force is superimposed, then I don't have fully reversed conditions that I would use. So we will deal with these in the next few topics of fatigue design.